Hey everybody, Dr. A here, and in this video we are going to be exploring an example of hydrostatic loading. So, hydrostatic loading is loading that is coming from some kind of liquid acting on something. In this case, we're going to be considering a structural flood wall, okay? And in general, hydrostatic loading could be considered a live load, it could be considered a dead load, it could just be considered its own category of loading. But regardless, we're talking about how do we get that value, how do we calculate what it is. So in this given statement, we are told to compute the factor of safety against overturning about the toe of the concrete flood wall. And we're given a unit weight of concrete of 150 pounds per cubic foot. That's the PCF. And then we're being told that the liquid that is being retained behind this flood wall here has a specific gravity of G sub S equals 1.01. So let's take a look at this. We have a section of a flood wall here, and the flood wall is only 5 feet tall, so it's not that tall, and it's 3 feet thick. So we can make a little note here. This is definitely drawn not to scale, okay? But regardless, this is 3 feet thick and 5 feet tall. And it's holding back this liquid, probably water, because specific gravity of water is about 1. And again, we're looking for the factor of safety against overturning about the toe of this flood wall. So let's go ahead and write a solution here. So in general, a factor of safety against overturning, we can call that sometimes Fs sub O for overturning, is going to be equal to a resisting moment, which I'm going to call M sub R, divided by an overturning moment, which I'm going to call MO. So we'll make a note here. This is resisting moment and then divided by overturning moment. And then also in general, if a factor of safety is greater than 1.0, the wall will not overturn. Okay, so of course, if the factor of safety against overturning is less than 1.0, the wall will overturn. It'll tip over, okay? So let's go ahead and get started. We're gonna redraw this figure down here, and of course we have our wall here, and it's 5 feet tall, 3 feet wide. Again, this is not to scale. Okay, and here's our water level back here. And so or the liquid level, I guess, but it's probably water. So on the back side of the wall where the liquid is, the wall is going to be exposed to this hydrostatic pressure distribution like so, okay? Where the maximum pressure is down here. And of course, based on what we know about hydrostatic pressure, the maximum hydrostatic pressure is going to be gamma liquid times the total height of the wall, okay? And so let's go ahead and calculate that. The unit weight of our liquid is going to be the specific gravity of the liquid times the unit weight of water. So that's going to be 1.01 times 62.4 pounds per cubic foot, or in other words, PCF, okay? So we're going to calculate that 1.01 times 62.4. That's going to give us 63.02 PCF. And then we can calculate our hydrostatic pressure at the base here of the wall as that unit weight of the liquid times the total height. So that's going to be 63.02 PCF times 5 feet. And we're going to calculate that as 315.1 PSF. Okay, be very careful. PSF, right? Because you have pounds per cubic feet times feet, and you're left with pounds per square foot here. So that PSF is a stress value acting on the surface of that wall, okay, acting on the back surface of this wall. And remember, we don't know exactly how along the wall is. The wall is coming in and out of the screen at you. So another way you can maybe sketch this wall if you want to visualize it a little bit better is we can sketch a 3D view of the wall like this. And we say dot, dot, dot because it's going on and on and on. And then behind the wall, we, of course, can show our hydrostatic pressure distribution on the back side of the wall. And again, this hydrostatic pressure distribution is acting all along the back side of this wall. Okay, so I'm just kind of sketching this here. And, oh, that's not a very good sketch. Let me try that again. Here we go. So you have this kind of stress distribution all on the back side of this wall. Forgive me, I'm no artist. I think I've never claimed to be a very good artist. So you have this triangular stress distribution that's basically like a 3D triangular surface on the back side of that wall, okay? And so what's happening is that pressure on the back side of the wall is causing a uniformly distributed overturning moment about the base. So right here, this is an overturning moment, and it's uniformly distributed along at the base along the length of the wall. Okay, so every linear foot is experiencing some kind of overturning effect. So the question is, how do we calculate that? Well, if we look back at our original figure, we know this is a triangular shape because hydrostatic pressure is linear increasing, okay? So we can have a resultant hydrostatic force right here. I'm going to call that P sub H. And that's going to be located at the centroid of the pressure distribution. So what's the centroid of this pressure distribution? Well, it's 1/3 of the distance from the back side of this triangle, or 2/3 of the distance from the tip of the triangle. So if I measure this pressure distribution centroid from the base of the wall, then that's going to be 1/3 times 5, so just 5/3. So that's 1.67 feet from the base of the wall. Okay, now how do we get this equivalent point load right here, P sub H? Okay, so let's calculate that here. Let me be a little more specific. This is maybe Y bar, and that equals H over 3 equals 1.67. There you go. How do we get P sub H? How do we get this equivalent point load here? Well, again, area of the pressure distribution. So we can come down here and we can say P sub H is 1/2 times sigma hydrostatic times the height of the wall. So that's the area of a triangle, right? So that's gonna be 1/2 and times 315.1 PSF. 315.1 PSF times 5 feet. So that equivalent horizontal hydrostatic pressure is going to be the following. It is 788 PLF. So this is going to be 788 pounds per linear foot. Now, be careful. This is pounds per linear foot. What does that mean? That means that you have 788 pounds here, and it's pointing at the wall, of course, just like I drew the arrowhead, but that's a uniformly distributed load coming in and out of the screen, okay? It's coming in and out of the screen at us, but it's directed at the wall. So think of maybe my really bad-looking 3D figure over here. It's a uniformly distributed equivalent load acting on the back side of the wall like this, and here's that uniform load here. Okay, so you got to do some visualization here. That's P sub H, and it has units of pounds per linear foot, and the per linear foot is along the length of the wall. So that's what I mean by coming in and out of the screen at you, or in and out of the page at you. So then to calculate that overturning moment, we just say P sub H times Y bar, and that's 788, again, pounds per linear foot, times Y bar is 1.67 feet. And once we multiply that by 1.67, we will get 1,316 pound-feet per foot. Now, you may be thinking, why don't we just cancel the feet in the numerator with the feet in the denominator? Well, mathematically, you could do that, but that physically won't make sense, because you want a uniformly distributed overturning moment along the length of this wall that I kind of sketched here already. So if you take that P sub H, which has units of pounds per foot, and you multiply it by its centroidal distance, this Y bar right here, then you'll end up with exactly what you're actually looking for. You're looking for a moment per linear foot. And that's what we've kind of sketched out here, a moment per linear foot. So that means that every foot of the wall coming out of the screen at you is feeling 1,316 pound-feet of overturning moment. So that's our overturning moment. Now, we need the resisting moment, okay? The resisting moment is a moment generated about the toe. Remember, this is the toe right here. Let me sketch that back on here for us. That's the toe. We want the resisting moment about the toe. So the resisting moment is what is resisting the wall from trying to tip over. Well, of course, what is that going to be? That's going to be just the weight of the wall itself. The wall's weight is going to resist its own overturning, right? So if you have a bigger, heavier wall, what is it going to be, easier to tip over or harder to tip over? Well, it's more difficult to tip over a big, heavy wall. So our question now is, how do we get this resisting moment here, okay? So what we first do is we need to get our weight of the wall per linear foot coming in and out of the page, okay? So how do we do, and notice the wall section is a rectangle too, so keep that in mind. So how do we get this weight, this self-weight of the wall, okay? Well, we've kind of explored this in terms of a dead load calculation before, but the self-weight of the wall is going to be equal to the area of the wall times the unit weight of concrete. And so what's the area of the wall? Well, that's that cross-section area of the wall is 3 feet times 5 feet. And then the unit weight of concrete is 150 pounds per cubic foot, or PCF. So the self-weight of the wall is going to be 3 times 5 times 150. And so that's 2,250 pounds per linear foot, okay? Again, you have feet times feet canceling with some of the feet in this denominator, so you're left with pounds per linear foot. So where is that in this kind of messy looking 3D sketch? Well, that's the self-weight of the wall pointing down. And again, that is a vertical distributed load that is coming in and out of the page at us in the section of the wall, okay? Now, we need the resisting moment, right? So how do we get the resisting moment about the toe? Well, you just multiply that W by its perpendicular distance to the toe, which is half of the wall width, 3 feet over 2, okay? So we're going to say the resisting moment is going to be this wall weight times the thickness of the wall divided by 2. So that's going to be 2250 pounds per foot times 3 feet over 2. And so that's going to be 3 over 2 is just 1/2, right? So we'll get 3,375 pound feet per foot. Track those units. And now we can say the factor of safety. Let's color coordinate a little bit better. Color coordinate. The factor of safety for overturning is resisting moment over overturning moment. And that will give us the following: 2.56, which is greater than 1.0, and we'll say the wall will not overturn. And that is the conclusion to this problem, and the answer that you're actually looking for is this factor of safety of 2.56, but I've added in a couple little extra bits of commentary. Thanks for watching.